Hello everybody, this is me again, Yusuf Saleh, chemistry teacher. We're gonna go on our mini lectures. Uh, we reached chapter 2, section 3, and it's about acid-base reactions. Okay, in acid-base reactions, actually we have some terms we need to have the meaning of them and understand their strength. So we have two terms, the most important two terms here. These two terms are conjugate base and conjugate acid. First, let's understand what is conjugate base. When an acid loses one proton, which means loses one hydrogen ion, it becomes its conjugate base. And the opposite is the conjugate acid. The conjugate acid, when a base accepts one proton, it becomes its conjugate acid. So we have a molecule of acid. After losing one proton, it becomes a base, and a base, when gaining one proton, it becomes its conjugate acid. So the conjugate acid, a branched acid that lost one proton. A conjugate, so the conjugate base is a branched acid that lost one proton, or a molecule or ion that remains from branched acid after losing what? One proton. Of course, the opposite is conjugate acid. Conjugate acid is a base of branched that gained one proton. Let's have a look on the reaction here. The reaction here is a reaction of hydrofluoric acid after ionization with water. So it's mixed with water. We know that hydrofluoric acid is a weak acid. It is a weak acid, and water is amphoteric. It reacts as acid with base. It reacts as base with acid and takes its strength from the strength of its company, which means the acid here is weak. So water becomes what? Becomes weak base. Weak acid, weak base. Let's have a look on the right side. On the right side, the acid lost one proton. So the definition here of the conjugate base is fit with it. Acid and its conjugate base. So we have here a pair. This is a pair, and this pair, we call this pair of conjugates, weak acid and its base. Also, water reacts as, here we have acid, reacts as base and has its own conjugate, which is H3O. So we have two conjugate pairs, hydrofluoric acid with a fluoride, acid and base, water and hydronium, base and acid. What about the strength of the conjugates? We agree that hydrofluoric acid is a weak acid. So its conjugate as a base, it's opposite to it, exactly opposite in strength. So if you have a weak acid here, you will have a strong conjugate base here. W refers to weak and S refers to strong. And we say that water takes its strength from its company. We have a weak acid, so water becomes weak base. Okay, water here is weak base. What about its conjugate? Its conjugate becomes the opposite, which is strong conjugate acid. Now we have in this reaction two conjugate pairs, hydrofluoric, which is the acid number 1, and the fluoride, which is the base number 1, water, the base number 2, and hydronium, the acid number 2. Let's have the next reaction. Now we will have the opposite. We had here weak acid, we will have here weak base. Ammonia is a weak base. Sorry. So we have a weak base here, weak base of ammonia reacts with water as acid. Also it becomes weak acid. We can see that water reacted as base with the acid and as acid with the base, and takes its strength from its company. We have weak base, so it becomes weak acid. What about the conjugates? Ammonia and ammonium cation, the first conjugate. Water and hydroxide, the second conjugate. And we have the weak reactants with weak species to left, so to right we will have the strong ones. So what about ammonia? Ammonium, sorry. Ammonium, is it strong or weak? Of course, depending on strength of its origin is weak, so it must become what? Become strong. So we have here strong conjugate acid. Also for hydroxide, the origin, water, is weak, so it becomes strong conjugate base. So how many conjugate pairs we have here? Ammonia and ammonium, base and acid, water and hydroxide, the second conjugate. Okay, what if the acid and base that react with each other differ in strength? Ammonia, which is weak base, and hydrochloric acid, which is strong acid. The conjugate of ammonia, the acid, is still strong, and the conjugate chloride is the conjugate base of the strong acid, keeps weak. So we have here weak base, strong acid, strong conjugate acid because it's opposite to its origin, and we have weak conjugate base. This is what we call the conjugate pairs. So let's recall the definition of conjugate acid and conjugate base. What is the conjugate base? Conjugate base is a molecule or ion of an acid that lost one proton. The conjugate base is, the conjugate base is a branched acid that lost one proton, and the conjugate acid is a base that gained one proton. Let's move forward and see what we have more. Okay. These details are about the reaction above, but we have one question here. Which direction dominates, which means which direction is most active? Of course, the direction from strong to weak. So, and the first and second reactions here, reaction of ionization of hydrofluoric acid, the strong conjugates are to right, which means which direction dominates? Of course, the backward. The backward, because the strong conjugates are to right. Also for the second reaction. For the second reaction also, the direction of strong conjugates dominate. Okay, now let's move forward and see what we have next. Okay, we have strength of conjugates we just talked about right now. HCl, strong acid. Water is a strong base because it depends on HCl. And strength here, so we have, here we can say we have a strong acid. This is strong acid, and this is strong base, because we said that water depends on its company in strength. So hydronium here will become weak acid, and the chloride will be weak base. So which direction dominates here? The direction that dominates is from left to right, which means the forward. Why? Because we have the strong conjugates are to left. Okay, now let's move forward. It's written here, the favorable reaction is always from strong to weak, from strong conjugates to weak conjugates. And we have another note in the reaction above, a chloride, Cl negative, is weak base and cannot compete H2O, which acts as strong base in acquiring proton. So always the strong conjugate, strong base conjugate accepts a proton. But we have a chloride in the reaction here. Chloride is weak. So it cannot compete water in accepting proton. That's why the dominate direction is from left to right, which means the forward direction. Okay, let's move forward. We have some questions here. Question here: in the reaction below, determine Bronsted acid and base, conjugate acid and base, as well as favorable directions of the reaction. We have here acetic acid. Okay, acetic acid, we all know that acetic acid is a weak acid and it ionizes only 1.2%. As long as this is a weak acid, also water will be weak. But weak what? Weak base. Water will be weak base. Here we have weak acid. Okay. What about the conjugates? We have weak acid, so its conjugate here is strong base. This is strong base. And water is weak base, so its conjugate will be strong acid. Which direction is favorable here? Which direction dominates? Of course, the backward direction, which means in the container of ionization of acetic acid, we will have a very, very high amount of non-ionized acid and very little amount of the ions. How could they decide this? How could they find this? This depends on the conductivity. When the conductivity of any solution is high conductivity, which means concentration of ions are greater, but the conductivity here in the solution of acetic acid is not very high, and the solution is not a very good conductor. That's why the concentration of ions much less than the concentration of the non-ionized acid. Of course, the answer here is written. Let's see the next one, next reaction. There's not next reaction, but just there's a clarification here. If the strong conjugate acid and the strong conjugate base are to right, so the dominate direction is the backward. We have another generally favorable reaction of weak acid and weak base is backward, but favorable reaction of strong acid and strong base is the forward. It is just repeating for what we just said. Okay, now I have a question here. The reaction below determine Bronsted acid and base, conjugate acid and base as well, favorable direction. We have HClO4. Okay, HClO4 is very strong acid. It comes exactly after hydroiodic. Hydroiodic is the strongest ever. HClO4 perchloric acid is the second in strength. So this is very strong acid. As long as this is a strong acid, of course, water, which is amphoteric, will react as strong base. Okay, we have strong acid and strong base, and we will have very high concentration of ions, ion of hydronium. So this will be weak conjugate acid, and this will be weak conjugate base. So which direction dominates? Of course, the forward direction, because we have the strong conjugates are to left, are in reactants. The answer here is favorable reaction is forward reaction, because HClO4 perchloric acid is a strong acid, and H2O is a strong base, because its strength depends on the strength of its company. Okay, let's move forward and see what we have. This term is extremely important. Amphoteric compounds. Actually, I cannot say that the term compound is fit to this, because we have many species are not compounds, but they are amphoteric. What is the meaning of amphoteric? Amphoteric means a species that can react in two directions. Two directions. It can react as acid and it can react as base. It can act as acceptor of proton and also a donor of proton. And we have many of them. The first one is what? Is water. Water reacts as base with acid. Also, it reacts as acid with base. So water is amphoteric. Okay. Now, in the second reaction, we have ammonia, which is base, and we have water. Water donates proton here to ammonia. Donates a proton. So it's a proton donor. Proton donor, which means what? Which means acid. And we saw that with sulfuric acid, it's a base. With ammonia, it is an acid. Acceptor of proton, donor of proton. That's why we say water is amphoteric. Okay, is water only amphoteric? No, we have many amphoteric species. We have some compounds such as aluminum hydroxide. I don't know if it's written here or not. Okay, aluminum AlOH by 3. Also, boron hydroxide. These are both amphoteric because they accept a proton and also they donate proton. It depends on the strength of the company. But most amphoteric species are ions, the negative ions that still keep one proton or more. So for example, let's have a look at here. We have HSO4. HSO4 can accept a proton and react as base. Also, it can donate the proton here and react as an acid. So you see, negative ions still have a proton to donate. Negative ions still have a proton to donate. So this is amphoteric. H2, sorry, there is here H2PO4. Also H2PO3. This is also amphoteric. Why amphoteric? Because it still have negative ions, still has 2 protons, can donate. Also, it can gain 1 proton and get back to phosphoric acid. So it is double reaction. Beside it, we have hydrogen carbonate. Hydrogen carbonate with strong acids become base, but with water becomes acid, and with bases, other bases, it become acid. And the rest of the negative ions that still keep 1 proton or more. So let's recall the definition of amphoteric species. Amphoteric species are species that can act as a proton donor or proton acceptor, and most of them are negative ions that still keep 1 proton or more that can donate. Also, they have ability to accept a proton. This depends on the company with which they react. Okay, let's see what is this question. This question is of elementary, which means elementary exam. Which of the following pairs are conjugate? How can we distinguish the conjugate pairs? If 2 species present and the difference between them is 1 proton only, 1 hydrogen only, they are conjugate. The one with the more proton is the conjugate acid. The one with the less proton is the conjugate base. So let's have a look. Here in the first pair, we have hydronium and hydroxide. Hydronium has 3 protons, 3 hydrogen atoms, but hydroxide has only 1 hydrogen. The difference here, 2 hydrogen atoms, so this is not a conjugate pair. Let's have a look on the second. Second, we have hydrocyanic. We have hydrocyanic and we have cyanide. We have hydrocyanic and also we have cyanide. Okay. Hydrocyanic, sorry, it has a proton to donate. Cyanide, no proton. So the difference between them is 1 proton. This is a conjugate pair. This is correct. This is a correct. Can we say now that we found the correct choice? No, not yet. You need to read most of the all of the options, all of the choices. Why? Because sometimes you'll find in the all of them or A plus B or B plus. So do not rush. Read them all and read them 3 times. Okay. Let's have the choice number C, or choice C. We have NH2 negative and NH4 positive. So we have 2 hydrogens and 4 hydrogens. The difference is 2 hydrogens, so this is also not the correct one, not conjugate pair. H2SO4 with SO4 negative 2. Sulfuric acid and sulfate, also the difference 2 protons. This is also not correct. So the only correct choice here is hydrocyanic acid and cyanide. This is the conjugate pair. Let's ask ourselves this question. Hydrocyanic is weak or strong? Of course, it's weak. What about its conjugate? Its conjugate cyanide is a strong base. So this is how can we distinguish the conjugate pairs. Okay, let's move forward and see. Another question, elementary exam, which of the following is amphoteric? We have carbonic acid. Carbonic acid, can it be or not? Of course not. Why not? Because it can donate a proton, but cannot accept a proton. Okay, HCO3, it can donate a proton, also it can accept a proton and become carbonic acid again. So this is amphoteric. What about carbonate? It can accept a proton, but has no protons to donate. So it is not. This is also not. Hydronium, it has a proton to donate, but can it accept one more proton? Of course it cannot, so this is also not the correct choice. So the only correct choice here is hydrogen carbonate, or sometimes they call it bicarbonate. Why? Because it has a negative ion and has a proton to donate. Okay, let's move forward and see next term. Next term is OH in a molecule. OH present in many species. Some of them are acid, some of them are not acid, some of them are base. What determines whether the OH in a molecule can donate a proton or not? Let's have a look on an example here. An example here, we have hypochlorous, we have chlorose, we have a chloric, and we have perchloric. Actually, this example differs with the example in your textbook, but it's very clear. Let's consider the structure. Here in perchloric, we have a chlorine, we have a chlorine here, chlorine that holds OH, but it is bonded to 3 oxygen atoms. These 3 oxygen atoms increase the polarity. We have partial positive here and partial negative on oxygen. So we have very high polarity on OH and perchloric. And increasing the polarity increases the attraction of the solvent, which is water, on the OH and facilitates breaking the OH bond and donation of a proton. Let's see the second one. Here we have also chlorine bonded to OH, but not 3 oxygen atoms. It has only 2. But still the 2, here is chlorine. But still the two oxygen atoms can cause strong polarity on OH. So this still strong acid. So we have strong acid, very, very strong acid. But here in chlorose, we have a chlorine bonded to OH, and it has only one oxygen. It can cause polarity, but weak polarity. That's why this acid is weak. The two acids here are strong, and chlorose is weak, which means the ionization of chlorose much less than chloric acid and much, much less than perchloric acid. What about the, let's remove this now. Sorry. Okay. Let's see the final one. We have chlorine with OH only. No oxygen. When no oxygen, the polarity here will be very, very weak. Then this is actually very, 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 very weak acid, and it ionizes about 1 out of 100,000. Here we have 100%, about 100%. Here is weak, maybe less than 10%. But here, out of 100,000 molecules, maybe one proton only donated, which means one hydronium only formed. So in a molecule, when OH present, the acidity or the basicity depends on whether there are oxygen atoms bonded to the holder of the OH. We have many oxygen atoms, high polarity, stronger acid, and we have no oxygen, very weak acid. Also, we have an example that mentioned in your book, and let's see it. Okay. Let's write the example here. We have an example in your textbook. We have two compounds mentioned, which first one is acetic acid, CH3COOH. Also, we have C2H5OH. C2H5OH. Let's compare between them in acidity or in strength. In order to understand that, we're going to draw the structure. In the structure here, we have carbon, another carbon, OH, 3 hydrogen atoms bonded to the first carbon covalently and cannot be donated. We have oxygen bonded to the carbon that holds OH. This oxygen can cause a polarity on the OH group, which means partial positive and partial negative. Despite the polarity is not very high, but it's still an acid and ionizes about 1.2%. What about, of course, this is acetic acid. What about ethanol? This is ethanol. Ethanol is not an acid nor a base. It's not an acid nor a base. It cannot react as acid, cannot react as a base. Let's see why not acid. We have 2 carbon atoms, the first carbon, the second carbon, and we have OH group here. Here we have CH3 and we have CH2 here. The carbon that holds OH doesn't have any oxygen atom to cause polarity on OH, despite there is polarity, but weak polarity. So this is acid. Acetic acid is acid, despite being weak acid, but this is not acid nor base. This is not acid nor base, which means it doesn't ionize or dissociate. Why? because the polarity here is not enough because there is no oxygen on the carbon that holds OH. This is all about the term or the topic of the compounds or molecules that have, the compounds that have OH group. Let's move forward. I have a question here. The question is repeating for the example I just done. We have the acetic acid is acid and ethanol is not acid nor base. Of course, the reason is in acetic acid, the carbon that holds OH has oxygen that causes polarity and facilitates breaking the bond between hydrogen and oxygen and facilitates donation of proton. But in alcohol of ethanol, the second carbon which holds the OH doesn't have any more oxygen to cause high polarity and facilitate the breaking of the bond of OH. Let's move forward and see this question from section review. Explain how presence of several oxygen atoms in a compound, let's remove this, a compound containing OH group can make a compound acidic. We will repeat this actually. Presence of oxygen atoms on the atom that holds OH increases polarity and facilitates breaking the bond and donation of proton. Meanwhile, when there is no oxygen, the polarity is not enough and the bond is very hard to break. Let's move to neutralization reaction. We all studied neutralization reaction and knew that a definition of neutralization reaction is the reaction between acid and base producing salt and water. But this definition is not very thorough, which means it's not complete. It cannot be applied on all reactions of acid and base. Why? Because when we say produces salt and water, sometimes the salt is soluble, doesn't precipitate. So the ions that form the salt are spectator ions, and you cannot say that they reacted and salt formed because the salt is not formed practically. The ions are aqueous and free. That's why the definition is not very deep. The best definition here for neutralization reaction is the reaction between the two ions of hydronium and hydroxide. We have hydronium and hydroxide producing what? Producing water. So this definition is correct for all neutralization reactions, the reaction between hydronium and hydroxide producing water molecule. As we said, because sometimes the ions that form the salt are spectator. For example, we have the neutralization reaction between hydrochloric acid and sodium hydroxide. They produce NaCl and water. Okay, water is liquid. But this is aqueous. Aqueous, which means the positive sodium and the negative chloride are free in the solution. That's why we're going to remove them. Why? Because simply this is aqueous and this is aqueous and keep aqueous. So that's why they removed, they cancelled. The only ions that participated are hydronium and hydroxide producing what? Liquid water. So this is fit with the definition. Definition of neutralization is the reaction between hydronium and hydroxide producing or forming a water molecule. Let's move forward and have a look on this question of general exams of 2011, I think second term. We have okay. A base, strong base, an acid, strong acid, producing a salt and water. But this salt contains nitrate. Any compound containing nitrate is aqueous. It doesn't precipitate. So this is aqueous and this is liquid. So when we dissociate them, we will have the hydronium from, hydronium. Of course, this is not balanced because we need two here. And so we have two hydroniums from two nitric acid molecules, and we have two nitrate. We have one calcium cation and two hydroxide anions. But actually the ions here, this was aqueous. To left, all are aqueous. To right, we said that the salts of nitrate or compounds of nitrate are soluble. So they get dissociated. This is aqueous and this is aqueous, but water is liquid. So they got removed, nitrate with nitrate, because aqueous, and keep aqueous, calcium with calcium. So we see here that in the net ionic equation, only hydronium and hydroxide produced water. And this is also fit with definition of neutralization. Let's move forward and see this question from elementary. Determine the acid and the base that form salt of sodium phosphate, Na3PO4. How can we decide this? Actually, whenever you see a salt, to left we have the cation came from the base. Add hydroxide to it. Add the cation, and the anion come from the acid. Because the salt is ionic compound composed of cation from base and anion from acid. Okay, so Na came from NaOH. The anion came from H3PO4. Sodium hydroxide and phosphoric acid. Add hydrogen to the anion and add OH to the cation. Okay, so here we have phosphoric acid and sodium hydroxide. Of course, we have here, let's have a look on the reaction between them. We have phosphoric acid with sodium hydroxide. They form what? They form sodium phosphate and water. Of course, this is aqueous. After having the overall ionic equation and the net ionic equation, the ions of the salt will be removed because they are spectator, and the ions of hydronium and hydroxide will keep, and these are the participated ions. And these two ions the two ions here are spectator. Okay, let's have a look on the final note here. All active metals are, just pay attention to this. How can you predict the products of reaction? We have here all active metals react with acids releasing hydrogen gas. Salts supposed to form a neutralization reaction. Salts supposed to form a neutralization reaction. It is not single replacement, it's double replacement. So let's correct this. We have here double. So here, double replacement. How can we decide whether these salts are soluble or insoluble? We must remember the 6 rules, the 6 guides we studied in chapter 1, section 1, insolubility rules. Double replacement reactions to determine whether it's soluble or precipitate. So for example, here is insoluble. Sorry, here is soluble, aqueous. But if we had instead of sodium here, calcium, for example, it would be insoluble and it precipitate. Okay, that's all for today's lecture. I hope you get benefit from it and see you next time.